Hi guys. Today what we're going to do is we're going to talk about bosons and fermions. Now, in thinking about bosons and fermions, we need to introduce the concept of non-distinguishable particles. So if we take, for example, that we have two bowls, and you can see them there, and these two bowls represent two different energy states. Then what we can do is we could take two particles and we can consider that these two blue spheres here are the two particles. Now, in case of bosons, they can exist in the same energy state. So there are three possibilities for where they're going to exist. So they can exist in the first, both balls can exist in the first container, or we could see here, hold on guys, I'm sorry, that both balls could exist in a second container, for the bosons, or finally, the balls can exist in both the containers. And, in those two cases, we'd have three possible energy states for the boson. But fermions are different. Fermions cannot exist in the same energy state. So the only possibility that we're going to get for an energy state for the fermions is that third state for the boson, as we can see it right here. But how do we kind of come about that conceptually? And what we can do is we can generally use a Gaussian expression to represent the wave functions of the two blue spheres. If we have a relative idea of their position, then the wave functions would model like this, right here. So we can kind of see here, and this is discussed in the first quantum mechanics text, that, if we kind of know where the particle is, we're going to get that spike, in the wave function graph. So you can kind of see here that we have the first particle, and it's really at a position. We can't say it's exactly at the position x1, but you can kind of see it's right around there. And then we have the second one, and it's sort of like around this position x2, and we're getting about that spike there for the wave functions. So the Gaussian that could represent this could be very simple, and we could write the equation as phi of x1 x2 is equal to ae to the negative lambda x minus x1 squared plus b e negative mu, which is just another constant there, x minus x2 squared. Now, if we consider switching the position of one of the particles, say from x2 to x1, to do this, we might want to let a equal b and mu equal lambda. As long as we swap the particles, then we can get the same function if we hold these conditions, which means that the probability of one of our exchanges is equal to the probability of the other exchange, which would give us really that the wave function x1, x2 implies that the wave function x2, x1. Now, if we normalize the wave functions, we can set them equal because the normalization equals 1. Now, why are we going this way? Like, why are we kind of like, we're writing the Gaussian, and then we're kind of talking about switching the particles here. And the reason why we're really going here is because we want to come back up to what we're generally talking about here. That these two states here, that when we get a boson, the boson can exist in these three energy states, but yet the fermion can only exist in one energy state. So by going through the switching that we're just beginning to talk about, that we're actually going to be switching x1, that sphere x1 to position x2 and x2 to x1 to get that interchange of particles, we're hoping to lead to the fact of understanding why the fermion can only exist in one energy state. And that's the thing, that they both can't exist in the same energy state. That's what we're saying. So we couldn't take one fermion and move it into an energy state where there was another fermion. And but with bosons, we can do those things. So this is kind of like where we're going with this, but kind of conceptually in a way. So now if we normalize the wave function, we can set these two wave equations equal to each other. And we do this because we know that the normalization is equal to 1, and we know that's the square. So we end up getting this situation here. We get phi of x1, x2 squared is equal to phi of x2, x1 squared. And if we take the square root, we can assume 1 to be negative, which implies that phi of x1, x2 is equal to plus or minus phi of x1 plus x2, where phi of x1, x2 is equal to the positive phi of x1, x2, which is considered the symmetric case, and symmetric cases give us bosons. So we would say here that this particular situation here, phi of x1, x2, is equal to positive phi of x1, x2. Oh, sorry about that. It's not x1, x2, it's x2, x1. Sorry about that, which is the symmetric case and gives us a boson. While this other one down here, phi of x1, x2 is equal to negative phi of x2, x1, which gives us what we call the antisymmetric case, or what we call fermions. Sorry about that little misprint there, but it is the wave function phi of x1, x2 is equal to the positive phi of x2, x1. We can kind of see it up top there. That was my fault in the writing of that there. Sorry about that. But anyways, now consider that I only want to move one of the particles into the, so consider that I only want to move one of the particles into the other's energy state. Let me just go back for 1 second here, because I'm not too sure that I stated this. I did state that the symmetric case gives me a boson, but the antisymmetric case, I just want to make sure that I stated that that gives us a fermion. So basically phi of x1, x2 is equal to negative phi of x2, x1. That's the case of the fermion. Now consider that I only want to move one of the particles into the other's energy state. I can let x1 equal x2. Then for the boson, we get phi of x1, x1 is equal to that positive phi of x1, x1, which holds the symmetry and tells us that the bosons can exist in the same energy state. But now if we do it for the fermion, we get phi of x1, x1 equal negative phi of x1, x1. The only way this can be true is if the wave function is 0, which would mean that the probability of finding a fermion in the same energy state would have to be 0. This is Pauli's exclusion principle. Now, this is a very conceptual way of looking at it, which is great for students. But what I really liked about this is if we go back to our problem set this week, and we talked about identical bosons and the energy states, we'll notice here that with this boson here, we've got this energy state here, which means that really that boson's existing in the same energy state that we're seeing here, ignoring spin, of course. But now if we go down here, though, and we take a look at this situation here, with the fermions, that's not even listed, that state, because the fermions really cannot exist in the same state, and that's why they got a different eigenvalue. So guys, we're a little bit out of time now, but this is kind of what I wanted to bring today. I really thought this was something that was really pretty cool, and it gives a good conceptual view of what bosons and fermions are. And there's some sites here that are listed. Of course, our textbook and a YouTube video that I access. So thanks so much now, and that's all, guys.